Welcome back to Topics in Statics. Today we're going to talk about vectors in 2 dimensions. We're going to get into the nitty-gritty of how to deal with vectors on an everyday calculational basis. In order to make it simpler, we're going to just deal with it in 2 dimensions to begin with. So let's jump right in. All right, the first thing is notation. You have to have a good notation to make sure that we can convey this information to another person. So the typical way we do this to indicate something is a vector. In your book, they use a boldface. Many textbooks use a boldface type to indicate a vector. If I'm writing it by hand, I can't write in boldface. And so I draw an arrow over the top of it. And that arrow tells me it's a vector. Right? If I want to talk about the magnitude of the vector, I do the same thing. In your textbook, it would be an italic face, same letter. Italic face indicates the magnitude of the vector. I would just write it without putting an arrow over the top. So if you forget to put the arrow over top of a vector, you're telling me something different. And finally, for a unit vector, I put a hat on top of it. A lot of times I use the letter U to indicate a unit vector, but I don't necessarily have to. Sometimes I do, sometimes I don't. So here's this simple little expression, A is equal to A U of A. If I was writing that by hand, I would write A is equal to A U hat A. And that just tells me the vector A is equal to the magnitude of A times the unit vector in the direction of A. Now, what's a unit vector? A unit vector, the word unit is very confusing in this sense because unit vectors have no units in the physics or engineering sense. This is the word unit used in a mathematical sense, just like a unit circle. A unit circle has a radius of 1. A unit vector has a length of 1. Essentially what a unit vector is its direction. It tells you what direction something's pointing. So how would you calculate a unit vector? I would take that little equation right there and I'd solve for the unit vector. So the unit vector in the direction of A is equal to the vector A divided by the magnitude of A. And that's how you calculate a unit vector. That's how I would find that unit vector. So putting things together, I can talk about a vector. I can break a vector up into parts, and I represent those parts by a sum. So the vector A could be equal to the vector A1 plus A2. That's fine, or A1 plus A2 plus A3. But each of those vectors on the right could be written as a length and a direction. So I could write the vector A is equal to the vector is equal to the magnitude A1 times a vector in the direction of U1 plus A2 times U2. Right? In Cartesian coordinates, I have standard unit vectors, and the standard unit vectors would be I hat and j hat. I hat points along the x-axis and j hat points along the y-axis. So in Cartesian coordinates, this vector A, right, let me write this by hand, A is equal to AX in the I hat direction plus AY in the j hat direction. And so I would refer to AX and AY as the components of that vector. To find the components, it depends on what information you have, how you find the components. Here's a picture of a case 1 where I've got the magnitude of the vector and I've got that angle, theta. So if you know what the magnitude is and I know what that angle theta is, I can calculate using trigonometry because I've got a right triangle there. So in that case, fx is equal to f cosine theta and fy is f sine theta. And all I'm doing is looking at that gray triangle and using trigonometry. Don't try and memorize this formula down here. It's going to depend on which angle you're given. If I gave you a different angle, for example, if I gave you this angle up here, phi, those sines and cosines would be different because it's a different angle. Same triangle, different angle. So don't memorize that. Understand how to get it from a triangle. Another way that you're typically given vectors in this class is with a little slope triangle. So in this case too, you'll notice there's that little ABC triangle drawn on the picture. And what they're telling you is that the big shaded gray triangle, which is made up of the vector f and its components, fx and fy, is similar to that little ABC triangle. Now, typically they'd give you numbers there. They'd be 3, 4, 5 maybe. So if it's a 3, 4, 5 triangle, in fact, let's do it that way. All right, let's say this is 4, this is 3, and this is 5. So they give me a 3, 4, 5 triangle in the picture. And then they tell me the magnitude of the vector. It's the force, so let's say it's 7 newtons. So then the question is, what are fx and fy? Well, when I say that two triangles are similar, what that means is that the angles are the same. So the angles in the ABC triangle are exactly the same as the angles in the force triangle, which means that the trig functions are all the same. The trig functions are just the ratio of the length of two sides. Right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So the ratio of the length of two sides gives me the sine, cosine, etc. So for this triangle, and I'm given in the picture, fx is a over c times f. The biggest mistake I see students make at this point is that they are given that little ABC triangle and they can't calculate angles. And then they go back later and use that angle and calculate sine and cosine. Well, I don't need to do that. I've already got the sine and cosine. Sine and cosine are just ratio of two sides. Use those ratios. You don't introduce errors in your significant digits by doing that. Coplanar force resultants. Typically when I talk about a resultant, it means I'm adding some vectors and I get a resultant. Here we're talking about forces acting on an object. I add those forces as vectors to find a resultant force. So the way you do that is you resolve each force into its x and y components, and then I add the respective components using scalar algebra, since they're collinear. Kind of obvious. So here's an example of that. Here's three forces. I break up those three forces into their components. You'll notice that the components, for example, F2x, that number, F2x, is just a magnitude in the x direction. It's a positive number, but it points to the left, so it's negative. So I had to put that negative sign on there. So there's the forces resolved into their components. So I can use a vector notation and add like components in that first expression. And I get the resultant Rx and Ry. Or I could do it in a scalar notation and get to the same place, essentially. In that lower case, the scalar notation, I'm doing the same thing. I'm just not using all the i's, I hats, j hats, all that. The other thing to notice on the scalar notation is this little plus and an arrow over there. And that's indicating which direction I've chosen to be positive. Same thing in the y direction. I've chosen pointing up to be positive. So now I've found these coplanar force resultants. So how do I find the magnitude of this resultant force? Well, I essentially use Pythagorean theorem. I go backwards. And this is how I find the magnitude and direction of that force from that information on the previous slide. When you're taking the inverse tangent, when you're doing any type of inverse trig function, you have to be very careful with signs, SIGN signs, because it's ambiguous. You have to be careful what you're doing. And that's about enough for vectors in 2 dimensions. That's just a taste. We're going to do more of this. It gets more complicated in 3 dimensions, but we'll save that for next time.